So we've got a heap of solves on the first challenge at the moment, so I'll just run through that one now for everyone who might still be a bit stuck on it. We'll just give you this challenge. So the first one is Caesar salad. We have 30 solves, so congratulations to everyone who's done that. There's many ways of solving this one, but the thing that you need to, I guess, first look at when you see the name of this one, which is Caesar salad, is that this is probably a Caesar cipher. And a Caesar cipher is basically where you rotate the letters in the alphabet a certain number of places, and then that gives you that the cipher text, basically. So there's many ways of solving this, but if you just grab something like CyberChef, which is a very useful tool for much more complicated challenges as well, which is why I'll use this one. There are also generic, more specific Caesar cipher website tools, but this one's more expandable. So if we just grab this cipher text here and we bring in the ROT13, which is really just a rotation of 13 places. It's a variant of the Caesar cipher, but the ROT13 actually allows you to specify how much you rotate. We place the cipher text as the input here, and then if we just start at 1 and increment the count until we get something that looks like useful text. And oh, there we had MonSec. There was MonSec, which is all our flags are in the MonSec format with the brackets. That's our flag. If we then go and copy that, place that in as the flag and solve it, and that's correct, and we've solved that challenge. If you have any questions, please let us know. Otherwise, we'll run through the next few challenges over the next little while as well. But if you get stuck, please raise your hand and don't wait for us to just go through the challenge. Thank you.
All right, so I'm going to go over the second challenge rather, Substandard, and which has got I believe 22 solves now. And also the third one, Cryptography Infallible, has only got 2 or 3 solves, so I won't go over it strictly, but I will give some hints and show an approach that could be used to solve it. So this one here, Substandard, gives you a pastebin link to a ciphertext here, and from the amount of text here, that's often a giveaway that it's not just a simple Caesar or shifting cipher, because typically so you can play around with all kinds of different transposition and shifting ciphers like Caesar and ROT13 and stuff, but you'll get nowhere with that. And so typically that means, in this case, the next thing you want to try is just a generic form of monoalphabetic substitution cipher. What that means is that each character maps to one other random character, but it's not strict. Like, for example, the letter A in the clear text, in the message, will always map to a letter, I don't know, F or something. It'll always be that, but there's no clear relationship between the two. And the first thing you can do is maybe go to the first typical trick you want to do is do something known as a character frequency analysis. So if you just search up, if you just look for a character frequency tool, you can look this up. And because, for example, this is using the fact that in the English language, the letter E is the most common out of all characters in sentences. And so whatever character comes up the most here, probably maps to an E. So if you put that in here, calculate. Okay, now the space bar obviously comes up the most, but you can just ignore that. Okay, here the letter Z comes up the most. So we need a tool to actually go through and start switching the characters over. The best tool I was able to find was, what was it? Now you can find these just by Googling them. And on here, you put in a ciphertext, and it will give you the ability to start going through. Like, for example, we knew for a fact that the letter Z maps over to E because that comes over the most. And so we can say that, okay, let's say Z maps to E. Now we start getting hints. Now the first thing we can do maybe is say that, okay, here the first word is the word KZ or something E. Now there's not that many 2-letter words that end with E that you could begin a sentence with. So let's just say, okay, we know that K maps to a W, and we start to get more of a hint. And for example, you might see that the word the comes up a fair bit, which is going to be the most common 3-letter word. And there's a whole bunch of little tricks you can go through there, looking at what pairs of numbers come up the most. I won't go through all of them, but there's giant lists online of these kinds of tricks you can use. But the first trick I'll show you is that you can just click the auto solve button. And that will do all that statistical magic in the background for you and figure out what the substitution alphabet most likely is. And so here we go. Now we've got the best thing it was able to give was the text. We stand today on the brink of a revolution in cryptography. The development of and so this is a and this is actually an excerpt from W. Diffie and H. and M. Hellman's paper, New Directions in Cryptography. And if you go through here, you'll eventually get a sentence here that I put in myself. This isn't from the original paper. By the way, the key is substitution ciphers rule with underscores here. So if we just, so MonSec. If we put that in here and put that in there, we should get the flag for that. All right. Now the second one here, it's only got 3 solves, but people seem a bit stuck on it, so I won't strictly go through and solve it, but I will give you a hint. The type of cipher being used here is a Vigenère cipher. And a Vigenère cipher is a bit more complicated. Funnily enough, a few centuries ago, it was thought to be completely unbreakable and resistant to all forms of cryptographic attacks. However, I think in the 1870s, I believe, someone came out with a general solution to solve them. But once again, this does rely on character analysis. But the other hint I'll give you is that in this case, the key is very long, and generally Vigenère ciphers are just an absolute pain to solve. And so whenever possible, I like to just skip the first step and just go straight to automatic solving. But I'll just give you a quick overview of how it works. So basically, the way it works is you get a, the way that these ciphers work is you start with a message. So let's say I'm trying to encrypt the phrase, let's say I'm encrypting the phrase, hello world. And the key we're using, we're saying, well, let K equals the string key, which is the password. And the difference is, in this case, the letter K maps on top of here, and it wraps, and it keeps on repeating. And so this is what's known as a polyalphabetic substitution cipher. Because you can see here, I can't remember the exact maths on top of my head, but like if you say let A equal 1, B equals 2, C equals 3, so on, and you add these two numbers together and then put the resulting number here, whatever that is going to be, I can't remember off the top of my head, but one thing to keep in mind is that in this case, for example, the letter L comes up twice in a row. However, they map to different characters because they've got the different key here, which is why it's known as the polyalphabetic substitution cipher, and it's not vulnerable to those kinds of attacks that we used previously. And there are still ways to break it. I wasted about an hour last year trying to go through and solve one of these manually until I discovered this tool that could do it automatically. This website here I found was quite good at solving them automatically. I won't go through and I won't actually solve it for you, but I'll just put you in the right direction, maybe switch it from German into English. And that's about it for now. I'll give you a bit of time to go through and work on some new challenges and let me know if you get stuck on anything. So how's everyone going? So I might have a look at some of the other challenges people are having a bit of trouble with. Like, for example, this problem here, Baby's Crib, has only been solved by one person. And so I might give a quick demo of how that challenge is laid out. So the first thing about the challenge is that given to you are two files, babycrib.py and output.txt. Now, within crypto challenges, this is a very typical format. They give you It's a very typical format. They give you a file, often a Python script that generates an output, and they give you the output of it. But often the original file will hide some information about it. So in this case, you're given the text, and you're given this thing here. And so from here, you can have a look at what the cipher is doing. So here it just defines a function, byte XOR. It's just a convenient way of XORing byte strings with each other. And here, the way it works is there's two messages, M1. Now you don't know what the contents of M1 is, but you know what a bit of M2 is. This string here, congratulations, the flag is MonSec and then the flag. However, you don't know the flag or the message here. And the first thing it does is it creates a random key K. Now urandom is secure enough, and so you can't guess that. And it gives you C1 is XOR the message with the key, and C2 is the second message with the same key. And so the way this works is that this is a form of attack on a one-time pad with key reuse, also known as a two-time pad. And generally that requires a bit of explanation of how the theory behind how that works. And so generally speaking, if you've taken Fit 1047 or if you've taken a discrete maths unit before, you might have seen a quick definition of XOR. So the way it works is XOR is a binary operator where if you've got two inputs, say A, B, A, B, and then A XOR B, you can draw a truth table here. The output is, if it's two inputs of 0, gives a 0 and a 1 gives a 1 and a 0 gives a 1, and a 1 and a 1 gives 0. So the way you can think of this is either binary addition, ignoring the carry, because 0 plus 1 is 1, 0 plus 0 is 0, and 1 plus 1 is 0 because it rolls over. Or you could say that the output is 0 if the inputs are different. And so generally speaking, there's a few characteristics of this. Anything XORed with itself, anything XORed with itself is going to be 0. Equals 0 for all A. And anything XORed with 0 is itself. Yep. And so the way this works is when you're encrypting when you're using a secure form of one-time pad or just any kind of encryption using XOR, the way it works is you get the message. So you get the message. Oh, bloody hell. You can get a message. I don't know why this keeps doing this. But if you get a message and you XOR it with the key, so the message, the plaintext message and the key, and that equals the ciphertext C, which is what we're given. However, let's say we've got a situation where the key is reused over two messages. Now, the reason a one-time pad is named as such is because the key can only be used once. If the key is reused, then you come into this kind of vulnerability. So you can see here we're given C1 and C2. So let's say let's say C1 equals M1 XOR K, and C2 equals M2 XOR K. Now, using those properties I mentioned earlier, what happens if we XOR C1 and C2 together? C1 XOR C2. The result we get is M1 XOR M2, because it's associative and commutative and that stuff, you can move it all around. XOR K, XOR K. Now, we already said that anything XORed with itself is 0, and so this cancels out, and anything XORed with 0 is itself. So this leaves us with the XOR of the two messages together. And so what we get is the two messages XORed together. And so what we can do is we can get a partial bit of the message that we know. For example, here we know that a part of the message here is this string here. And if we XOR that, let's say we know a bit of M2. For the bit of M2 we know, if we XOR M2 with it, that will cancel out and will leave us with M1. So however long of the message of M2 we know, we can calculate that bit of M1. And you can do this manually. However, there are websites that can help you do methods of crib dragging. And so the best website I was able to find was, I don't know, I'm trying to remember what it was called. Yep, this is it. And so what you can do is you can just paste in the hex of both messages. So let's say you put in the message here, message here. Now, if you don't know any of the message, you can do things like searching space, and then other kinds of messages that you might think come up. But in this specific case, we know the flag format and we know the message that is given to the user after the flag is found. And so what we can copy is this string here. Congrats, the flag is MonSec, this much. And so we guess this. And we can tell that part of the other message is the string, the quick brown fox jumped over this. And so now we can kind of go back the other way because we can reasonably guess the output of the second thing. We can say we can go through here and guess that this comes from here. And so the flag here, including and because it has a full stop at the end as well. I think if you included the full stop would have come up, but now it's not resulting. But the flag in the end is MonSec don't reuse keys. And if we get that, finish the format, then that should work. Are there any questions? Anyone unsure about that? Do we have, hang on, are there any other challenges people are particularly stuck on, anything that they would like me to walk through? Has anyone done any of the keygen challenges out of curiosity? Yep. Yeah, I saw one person solve this first one, but I haven't seen anyone solve the second one. Actually, no, someone did solve the second one. Was that you? Oh, congratulations. The hint I'll give, that one includes XOR as well. But if you're not familiar with that, if you want a good introduction to the basics of reverse engineering, the keygen challenges are good. Otherwise, I'm particularly fond of RSA, so they're a good thing to get started for cryptography. Now I'll have a quick break, let people work on whatever it is they were working on before. They put in the flags that I showed. Hint on RSA, right. So, hello, mystery Zoom man. RSA, yep, oh, hang on. Yeah, I'll close that. So, RSA1, the best hint I can give to you is figure out what exactly you need to solve it. So if you just go to the Wikipedia page for so if you go onto the Wikipedia for the RSA crypto system, it'll give you, there's a tab down here for the operation of it, and it'll tell you the formulas for encrypting, decrypting, generating keys. I'll give you a quick overview. You might have recalled some of the formulas if you did 1047, but generally speaking, the formulas for the message and so if you've got a message, M is the plain text message you want. We raise it to the power of E, reduce it mod N, and that is equal to C. And then to convert C into M, we say C to the power of D, which is known as the private exponents, mod N equals M. Now, there's a few interesting properties to know here. E is a fixed value equal to 65,537, which is quite, like, I think 93% of the time in all crypto system, whenever RSA is used, this is the value of E, 65,537, I can't remember exactly. But N is equal to the product of two prime numbers, so called P and Q, equals P times Q. And D is the interesting one. D is the only bit that you don't know, and if you figure out what D is, then you can decrypt it. So D is equal to what is known as the modular multiplicative inverse of E. There are calculators to do it. Basically, it just means the number where if you multiply it with the other number over a modulus, it would be equal to 1. And so basically, you can say that D and E cancel each other out. So D, e to the negative 1 mod. But here's the interesting bit. It is mod a function known as phi of n. Now that's phi of n. It means an Euler's Totient function. There's a lot of number theory in it. I don't understand half of it. But generally speaking, in this case, phi of n is equal to p minus 1 times q minus 1. And so generally the steps are, first, you need to find the factors of the modulus here, p times q. Now, generally speaking, if the factors are small, so generally around 256 bits or below 500 or something small, like if it's less than 1024 bits, generally you can assume it can be broken in lots of these challenges. Once you get the factors, it's more often than not, it's all over. Then you calculate phi of n, then you use that to calculate d, then you use that to find this and calculate the message from that. And in this specific challenge, you can tell that the message here is encrypted using this, and you can convert between decimal numbers and ASCII strings using CyberChef, but there are similar Python functions you can find to do that. Generally, it's fairly straightforward once you actually get the value of M. RSA2 is similar. Also, I'll give you one quick tool that's really interesting. I'll give you a quick demo. The value of n here, the value of n here is 200 bits, which is way less than is typical. Like RSA, generally the industry standard is a minimum of 1024 bits, which means this can be broken. And if you want to find what the factors of this are, you can go to a website called FactorDB. And generally speaking, if a number is small enough, FactorDB will contain the factors of it. However, in this case, it does have the factors, but for the sake of future CTFs, if a number is large enough that it doesn't have factors already, but small enough that you can compute it, The Alpatron factor calculator is the best one that I was able to find. It uses the Euclidean, elliptic curve method to factor integers for you, and that should run for a second. Yeah, and that's already solved it. Those are the factors of it you can calculate. And just from there, you can just follow the steps on the Wikipedia page for the RSA crypto system, and you should be smooth. What else? I noticed nobody has gotten password protected too, so I might just give a quick overview of it. Actually, how many people have gotten password protected 1? 27, yeah, so I'll give a demo of that now. Password protected 1 is a website. Please get into the password to continue, test, login. Sorry, wrong password. And generally, you want to try and figure out how is this password being verified. In the ideal situation, the password is being sent off to a web server, it is being compared to a hash, and it is being validated or not. But in this case, because I don't have access to the back end of the CTFD platform, I had to do it all on the web page. So if you go into the source code here, you can find this function here, login. So the way it works is there's this function here, login. Type in. Here's the actual password inputs, and then onClick equals call login. And the function login here, it says if document get by ID password. So basically, if the password you entered is equal to this flag here, then it says alert, and it means tell you that the flag is valid. So basically, you can figure out what the password is in this case by checking here. Oops, I copied that wrong. Yeah, and ideally, oh sorry, that's the wrong password site. Yeah. No, I copied it wrong again. And yeah, that is the right flag. And password 2 is a bit more complicated. If you look at the source code in the same way, you might go down to here, but you might notice that instead of the password being compared directly, it is being compared to a password hash. Now, in this case, it is using a hashing algorithm known as SHA-256. And so the trick is here, you want to try and figure out what the password of the hash was that went into it. What the password is from the hash. Now, typically the first thing you do is you'd Google it or you'd go onto CrackStation or something. But in this case, the hint it gives you is that, but in this case, in the password protected thing, the password is in this format of the MonSec flag format, which obviously wouldn't have come up in the password breaches before. However, the hint it gives you is this comment from one of the developers to switch to two-factor authentication instead of password-based authentication, as most users have very common passwords. And so the solution I was able to find was to actually write a script and just check a lot of passwords. If I recall correctly, it was like the 30th most common password, which is enough to technically do manually, but I'd want to do it with a script anyway. So the best, and if you look, I think I forgot to release a hint on this one. I might do that in a second, but if you look at something called, there's a thing called the RockU password list, and it's basically a giant list of passwords that have been, actually RockU was I think a website that suffered a breach a while ago and had a whole lot of passwords come out, and because it was such a large amount of passwords, it's a starting point for people trying to crack passwords, because this contains a lot of very common ones. So once you download this, you can write a script on here to just go through and try a whole bunch of the hashes. I won't bore you with debugging it live, but ideally so this thing here, you want to find a value such that SHA-256 of the string MonSec, and then something here is equal to this hash here. And that should take about, on my computer it took about 10 seconds to find, but that mainly included the time it took to import the RockU password list. But it should be straightforward once you figure out the format of the challenge. And I apologise if this was a bit too open-ended. Any questions? Are there any? I'd be keen to see if there are any challenges people were particularly stumped on, or things that people were, or challenges where people really wanted to see what the intended solution was, or people don't know what to do, or maybe they think they're almost there. Because I threw these all together this morning, and I'm not sure how good half of them are. All right, so I'll. Sorry? Time to seed. Oh yeah, time to seed was a bit more of an interesting one. I'll close some tabs just to clean some stuff up. So time to seed. So again, it's a typical format. It gives you the output. And it gives you the script here. I've already got that open. So what have we got? Time to seed. And we've got our output here, which is just a byte string of bytes. And we've got this. So the first thing is you've got the same function here, byte XOR return, like this just XORs two byte strings together, and it's just a helper function for us. And the thing we've got again here is the same flag message, congrats, your flag is MonSec this, which is the same thing we saw in the crib dragging 2-time pad test. But the interesting thing here, now one quick recap, whenever you're dealing with XOR encryption, when it's broken, which you're assuming it is broken if it's in a CTF, there are 3 things that need to be broken, that can be broken about it, 3 conditions that must be held in order for it to be unbreakable. First of all, the password must be original, which is what we broke in the previous one. The password must be the same length as the ciphertext, as the message, which we're assuming it is in this case. However, the third condition is that the password must be unpredictable. And if you can see here, this phrase here, random.seed int time. And that's the interesting one, because generally, the way that seeding random numbers works is that if you know the starting condition of the algorithm that is being used to generate random numbers, you can predict the future results of it. And so figuring out what the starting seed is can usually help you figure out what the next numbers generated are going to be. Now, in some cases, some crypto challenges will give you some huge amount of outputs and you can use that to reverse the seed. But in this case, we're going to do the opposite. We're going to figure out the seed. We're going to try all the seeds and compare it to this. Now, in this particular case, because our computers are quite fast, we can just literally just go through and try every single integer second within the last 2 years. I personally generated this seed, this challenge at 8:41 in the morning, and so I shouldn't have to check back that far to solve it. So here's the general solution that I was able to find for it. So what did I have here? Yeah, so the first thing you want to do is you want to, actually no, I'll just make a new file here, it's easier. So the first thing you want to do is you just want to copy the output here. So let's say C equals this. And we also want to import time, because they're the 2 libraries that we use. And the first thing we want to do is, what we can do is, the general method we're going to follow is we'll generate a number, which is, so this is all centering around what's known as Unix or epoch time, which is just a single number that increments every second and is used to store time. And so basically one of these seconds was used to generate used to seed the random number generator. We just need to figure out which second it was. And the way we can do that is just by checking one of the seconds and seeing if it was the one used, by checking to see whether it generated whether it XORed with the ciphertext generates the first bit of this. If not, check another second and just keep doing that until you find the right seed, and then use that to predict the rest of the message. So the first thing you do is you just create a helper function, I don't know, seed, because this is being used to generate seeds. So the first thing you do is you seed it using that, and then key equals bytes. Now we're using 9 because we can just take a shortcut and only generate the first 9 characters, because we're just comparing it to the phrase congrats and seeing if that comes up. Because if we've done it properly and the first 9 bytes we get when XORed to the ciphertext creates the string congrats, we know we've found the right seed, and we can use that to generate the rest of the rest of the bytes used to decrypt the entire thing. And so we can say if key equals yep, that's that. Now in this case we can just go through, you can go backwards. I'm just going to assume it was created in the last 2 years, even though I know it was created in the last, I don't know, 24 hours. I can say for I in range int time.time minus I think the number I had here is 172,800. That's about, I can't remember how long it is, but it's a long time. And int time, not time. Actually, that's the amount of seconds in 2 days, I believe. If check I, print I. And so if we run that, we can see if we can find this. We can see if we can find this the seed used. Oops, what did I do wrong here? Now it's a law of nature that these live coding demos always break. I'm not line 15. Hang on. Oh, thanks. Output not defined. Where did I do that? Hang on. Oh, hang on. What did I do wrong? Oh shit! I think I had a line here. Oh no, sorry. Yeah, no, that's right. I forgot here. The output I was supposed to define here. Output equals byte XOR. We want to compare the first 9 bytes of this with the phrase congrats, and so we can just do byte XOR congrats and see the first 9 bytes of this, and then we can check that to see if the first 9, because as I said, you know, because it's kind of, you can use XORs to go back to find keys from messages and vice versa. If we XOR congrats with the first 9 bytes of the ciphertext, we can find the first 9 bytes of the key. And if we seed it right, then the first 9 bytes will be the key that comes up here. And so if you run that now, fingers crossed, I equals, fingers crossed, byte XOR. Oh yeah, I forgot to copy that across. Now, fingers crossed for a 3rd time. I always forget something. But what? Hang on. Oh, that's right. Yeah, that's to go down here. Yep. Yep, that should be running, and that's just checking every single second. Oh shit! Hang on. I don't know what I've done wrong here, to be honest. This is the crux of CTFs: is problem solving and just trying a whole bunch of stuff and figuring out what you did wrong. Can anyone figure out what I did wrong? I'm sorry if this is a Brian, right? Yep, so I might just leave it here. So what I'll say is that what you want to do is you want to, thank you, but what you want to do is you want to, you know the range of numbers which the seed exists, and so you want to try every single seed value until you find a result of the seed that is expected, and then once you've got that, you can verify that the seed was used exactly. So what you can do is you can reset the seed of the random number generator to exactly this position, use that to XOR it with the entirety of the output, and you should get the entire message, including the actual flag here. And I'll leave that as an exercise to the viewer later tonight. And yeah, I don't know if there's much, hang on. Yeah, 12 people got Stegosaurus. That's, if you ever see the phrase Stegosaurus come up in a CTF, it's a hint of steganography, if anyone's familiar with that term. Yeah, people are actually doing a lot better in the CTF than I was expecting. Because it's impossible to tell how difficult a challenge is when you're writing it yourself, because in your mind it's got a clean solution, but obviously no one knows what it is, and it's annoying. Yeah. So has anyone got any questions or any topics in particular they wanted me to cover? Anyone? All right. If no one's got any questions, I might just for the benefit of the one person that solved the second keygen challenge, I might give a quick walkthrough of that because it's probably a topic that people haven't really looked at before. Now, this is a quick introduction to reverse engineering, which is where you're given a compiled file. Like for example, in this case, you're given a Python source code, but in this case, it's written in C and it's compiled, so you can't exactly look at the source code exactly. You need to be a bit more clever. So once you save that, right, I'll save that. Yeah, so if I just got a lot of windows open. So what you want to do is you can use whatever disassembly you want. I like IDA, but another good one is Ghidra. The difference is Ghidra is free and open source and it comes with its own decompiler. IDA costs an absolute ton of money, but because I'm being recorded, I won't say how exactly I procured this piece of software. Yeah, exactly. I mean, so it doesn't have to. Like, if you can use IDA freeware, but it doesn't come with the disassembler. You can just look at the assembly listings. So the way this works is, so the first, so the way this works is, it will look at the assembly listing of the file and give you a general look through. So when you run the file, where am I? I'm just going to open the desktop. So the way this file works is that when you run it, it'll ask you for the product key, and it'll say that sorry, that flag was incorrect. And what you want to do is you want to find out what that key is. And so you can go in here. Generally, you can look at the thing here. It's using assembly, so it's using these instructions to say enter your product key, and then it's calling enter your product key. It's calling this function as scanf. Saving in a variable named password and calling a function called validate. And you can see from these arrows the directions it can take. Either it's going to call the phrase, congratulations, the flag is that, but we don't know what that is because that's just a format string that hasn't been filled in. Or it can call, sorry, that flag was incorrect, and then it exits. But we just need to find out exactly what the flag is. And you can tell that the bulk of what this is going to be done in the function here named validate. Now, if we go into this function validate, it looks like an absolute mess. So we press F5, decompile it. And it still looks like a mess, but a bit more of an approachable mess. And the difference is here you can define, like IDA's not very great at making these things really readable. Now, I have gone, hang on. Now you can tell here that the way this function is being it takes a bit of time to understand this, but generally the way that this is being, what this function is doing is generally, you've got a function, say, int. It's Java. And so I won't make like the full set of source code. It's got something called key, and it's got some kind of key in it. And then it's got base. And then what it is doing here, you can tell, it is looping over from 0 to 30, and it's saying and it's looping over each of the one and saying and checking, and basically on every single check, it's checking to see if password XOR base, XOR key equals not equals base. And so generally this is a form of XOR like this is very common in keygen challenges, and so I'll save you the time, but basically what you want to do is you want to XOR these two strings together, and after you've done that, because of the the properties of XOR that I covered earlier, you should be able to get the key back from it. And so once I'll save you the trouble of actually I'll just go through and do it quickly. Let's say you've got two lists here. You've got key equals 0. Then you got base equals 0 times 30. And then what you can just do is go through here and copy the instruction listings here because the syntax is close enough to Python. You just need to do some clever formatting. What you can do here is just go through and copy each of these lines. And then what you can just do is do .join, and you're just XORing each of these lines with each other, one character at a time. Yeah, and you should get the flag from that. And that's an introduction to reverse engineering, maybe a bit of a convoluted one, but that's something you can work towards now that you know the general approach to take with that one. Any questions?